It's my pleasure now to introduce Dr. Stan Bovid, who serves as the Director of Materials Research at LSP Technologies, where he's manages the application development and engineering for customers and oversees the company's Materials Science Center of Excellence, which offers a wide range of testing and materials instrumentation to reveal the strategies and benefits for improving metal components. Stan earned his PhD at Ohio State University, kind of focusing in on the aspects of laser peening. But I will say that I think one of the things that Stan has really been a champion at LSP Technologies is developing our ability to model and simulate the capability for laser peening. And I think it's the part of the process that is helping to really implement the technology in the areas that our customers are now wanting to apply this technology to improve the life of their components. And with that, I'll let him talk a little bit more about what he's got going here in terms of peen forming and shaping, using some of the information and knowledge that he's pulled together and has helped so much guiding us in our efforts with deploying laser peening as a very unique tool to solve a lot of challenging problems. Stan.
Thanks for the introduction, David. Good afternoon or morning or evening to everyone else out there, and appreciate everyone spending some time with us today. The focus for the presentation today is on laser peen forming and shape correction. So with that, I'll just kind of dive right in some of our content related to those two different processes. They're very similar, and we'll kind of delineate what the differences are as we go through the presentation. So as you've probably heard earlier in the conference or through general awareness of laser peening, can be used to extend service life of parts. That's the most common usage of the technology, but it can be also used to reshape and straighten parts, and additionally to create complex curvatures or to manufacture desired shapes. Some of the benefits that you see if you actually use it for shaping and forming is that it's predictable, because all of the laser peening process is numerically controlled through the robots, through the laser peening system software. Each individual shot can be tailored to specific locations, specific process intensities. This also makes it very repeatable. As a forming technique, laser peen forming is very scalable. So if we start with coupon level studies, those can directly translate into our final product. And one of the ultimate benefits for peen forming is that there's very minimal tooling for many applications, which cuts down on the development timeline as well as the cost of creating perhaps limited run shapes or very challenging shapes for other technologies. What we want to focus on for this presentation is going to be the reshaping and straightening, and then as well as creating parts with complex curvatures. So manufacturing processes induce residual stress during their usage. So whether you're machining, welding, heat treating, or applying surface treatments like we do with laser peening, you're inducing residual stress, potentially eliminating residual stress with some of those other treatments. But all of that can lead to changes in shapes as those processes are applied. With laser peening, it's an engineered process. So we're able to correct the shape of parts if we desire and form them. So that's applicable to shells, skins, plates, integrally stiffened panels, structural components, and other mechanical components. As far as actual abilities of laser peening compared to some other technologies, the most comparable forming technology that we can look at is shop peen forming. And advantages that LSP forming offers over that, there's several. One of the first is that there's no contaminating media with laser peening, so we don't have to worry about shot getting stuck into any chambers within a part, or potentially transferring down the line into actually causing some FOD issues. As I mentioned earlier, there's minimal tooling that we have to work with, which makes this fairly simple to implement into a lot of applications. Because laser peening has our deep plastic strain profiles that was discussed earlier in some presentations, we're able to achieve forming magnitudes that are far greater than shop peen forming. So just as an example, on the right side of the screen here, we have the radius of curvature that can be generated as a function of sheet thickness for different aluminum alloys. Showing the capabilities of peen forming, radius of curvature is one of our most common, and just as a reference to get everyone on the same baseline as to what that means, when we take a strip of metal and process with laser peening, we can put in a one-dimensional curvature as long as that strip is relatively thin. The tighter that you can bend the sample with that laser peening will give you a smaller radius of curvature. So in this case, having a smaller radius of curvature is a better indication of forming capability. And with laser peen forming, this is about a 10 times tighter bend radius than we can get with shop peen forming. There's some other benefits as well, using shockwave loading instead of direct cold working that you see in shop peening. So we have minimal change in our material properties from laser peening. So there is a small amount of cold work that goes in. However, on a percentage basis, that's usually on the order of about 10% with laser peening. Shop peen forming often is up 30% or greater. This low cold work level also helps with some of the stability of the processes that we can touch on in some additional slides later in this presentation. So most of the conference has already covered the mechanics of laser peening. I don't want to spend a lot of time on the actual process and how it works. So just as a quick summary, the laser is used to create a plasma. That plasma has a pressure which generates a shock wave inside of the material. And then that shock wave induces a plastic strain gradient in the material. Michael Katura's earlier presentation presented this conceptualization for residual stress, this elastic response of the material to our plastic strain. This is a great introduction as to how residual stress is formed. When we start to look at peen forming, it gets a little bit different. And just to consider why that is, there's a plastic affected volume of material. There's also the elastic affected volume. And we show in our previous diagram that this is a nice, simple lateral relationship, whereas this sample stretches out horizontally. The actual response is also horizontally. That's not the actual case, right? If you consider a full field approach to this laser peen forming, there's a lot of bending that also can go on inside of these elements. And if our volume of material is insufficient to handle that bending moment, instead of developing residual stress, or perhaps developing your maximum residual stress, that'll lead to bending of that structure. So essentially, within a processed area, you've created bending moments, which will lead to the distortion that we see. Because laser peening is an engineered process, this can be tailored to the amount of bend that you want, and as well as the location where you want it to occur. When this process is applied, it is not a one-dimensional bend that is created naturally. The laser peening process is mostly going to be a multi-directional bend. So the plastic strain is distributed radially out from our spot center, if you will, which is going to induce bending in all directions. So that is the natural output, leading to the creation of compound curvatures naturally from the process. As far as how we control laser peen forming, our tools are very similar to what we see in the actual laser peening process itself. As I kind of alluded to in that earlier slide, this isn't just about the laser peening parameters for forming, it's about the geometry that we're working with. So fundamentally, between laser peening and laser peen forming, there's not much difference. Really, the processes work similarly, and it's just how the actual material responds to the process. So we can control our intensity through selection of power density. As we increase power density, we get a bigger bang in our material. Shown on the right side of the screen is how our power density influences residual stress. Similar characteristics are developed as a function of forming. And then as a second lever that we can pull to tweak the process is the amount of layers that we apply to the process. So adding layers is going to increase potentially the magnitude of the treatments, the plastic strain that's created, and also extend the depth to which the plastic strain is reached inside of a material. Getting a little more specific into demonstrating this for peen forming, the maximum deformation that we're going to be able to achieve with peen forming depends on our material thickness. And as I mentioned, by adjusting our parameters, we can control anywhere in a range of 0 curvature up to a maximum radius of curvature for a thickness. So on the top right of our screen here, what we have is a 4 millimeter thick sheet of aluminum showing the function of increasing treatment layers and how that radius of curvature changes for a given treatment. This is eventually going to hit a saturation limit where we're not able to form this curvature anymore. And that's really where our shockwave has done the absolute maximum amount of work that it can do inside of a material for the conditions that we're using. The bottom right, we're just showing the thickness effect for a set laser peening condition basis. So at 4 millimeter thick samples, we're able to achieve the 0.22 meter radius of curvature. When we start to double and triple those, we start to have the forming limit is a lot less. So we're not able to achieve as tight of radius of curvatures. If we need to, as I mentioned, there are some alternatives in laser peen forming because we're creating a multi-curve process. We can actually add some other constraints into our system that could get these a little bit tighter. And in some ways, it's cheating as the process capabilities. But by pre-straining the material, you're actually able to increase the capabilities of the process as well. So one of the questions that we're going to run into in peen forming is kind of the process boundary limits. And what does that look like? So peen forming, we can demonstrate up to greater than 25 millimeter thick samples, so inch thick samples, and still form. Our actual upper limit is going to depend on a multitude of factors, right? So we have the thickness of the material we're working with, the alloy type, as well as its actual strength values associated with it. Different lasers are going to be able to peen form to different magnitudes, and then whether we use pre-strain. Then the other thing to be cognizant of is just the part shape that we're working with. The lower limit on peen forming has some similar issues. As we go to very, very thin structures on the order of maybe 2 millimeters under that, you potentially have an issue of having a uniform plastic strain field through that wave propagation, in which case you'll have almost zero bending. And in some cases where we have thin enough sheet combined with our laser peening conditions, you could actually get enough reflected shock waves that you'll bend the opposite direction that we typically see in our thicker structures. So how do we know if a material is a good candidate for laser peen forming or not? There's not a manual out there for laser peen forming. So one of the things that we have adopted is to evaluate relative capabilities for different alloy groups. And as we discussed in those earlier slides, if we consider that the peen forming ability is going to be based on the elastic response of the material, we can look at the elastic properties of the material in relation to its actual strength values to get an idea of how much elastic strain energy basically can be stored inside of a peen formed material. So breaking this down into a simple, this is an omega parameter. This is not a material property. This is an internal designation that we use, which is the yield strength of the material divided by the elastic modulus. we can group materials into how they will perform. And as you can see, our best benefit just on this relationship is going to be when we have a high ratio of yield strength to the elastic modulus of the material. This is why high strength aluminum materials work very well for peen forming, whereas, for instance, soft steels are a much harder material to peen form. Ultimately, there's a lot more that goes into it than that. As strength increases in materials, you still have to make sure that we're generating shockwave pressures that are a high enough magnitude in order to generate the plastic strain leading to this entire process. So there's the Hugoniot-elastic limit that we need to consider, this shockwave duration and the decay. There's a session tomorrow on modeling, and there's several other sessions on peen forming and straightening that may discuss some of these issues, but most of this will probably come up in the modeling discussions tomorrow if you're interested in learning more on these. So I wanted to spend some time to talk about how LSP Technologies goes through the forming application development process, what that looks like, and then potentially how it could be integrated at other facilities or for other applications. So in peen forming, we can do basic analytical calculations for one-dimensional curvatures. Basically, the maximum height that can be created is going to be proportional to the squared thickness of the sample. We have basic analytical models that could tell you that type of information. Once you get into anything more complex than a 1D curvature, this really has to be done through finite element methods. So a little bit on our finite element modeling process. For peen forming, our tendency is to use what's called the eigenstrain process of modeling. That'll be covered later, but essentially how it works on the slide shown here, the red areas represent where we are applying laser peening to our component. The gray area is just your untreated material. So in this case, we have a 5000 series aluminum plate. It's about 12 millimeters thick, and we prescribe a treatment on the top and bottom. We then evaluate what the predicted deformation profile looks like for this selected LSP treatment, and then we can verify that deformation profile through actual physical processing. This approach to modeling is the same that we use in peen forming as well as inside of our shape correction process. So jumping into the peen forming for shape correction, kind of a couple use case examples to walk through just to provide a synopsis of how this might work. So one of our applications is in a surface treating a Wankel engine crankshaft to benefit the life improvement. There's a challenge associated with this type of geometry where you have this eccentric lobe in the center, and through all of the manufacturing processes that go on in the shaft, there's heat treating, there's machining, they all induce different levels of deformation. And by the time that these crankshafts were received for us to treat, there's no tolerance left. And so we have a very tight tolerance window to work in on a part that already has very tight tolerances. And so if we look at what laser peening does to this type of geometry in the within our internal structure, as having a cross-sectional view of this crankshaft, our issue comes in where we have our residual stresses or our misfit strain are distributed unevenly around the center line of the crankshaft because of this eccentric lobe. What this does is creates this upwards curvature in the shaft, and ultimately we have a runout of 50 microns on this crankshaft, which in order for this to be acceptable to run inside an engine, this value needs to be below 10 microns of runout. So what we can do with the modeling process is essentially go in and identify treatment areas that will help to balance out this misfit strain and then compensate for the bending. So this is our corrective treatment example where we're down from our original 50 microns to 4 microns of runout. And this works out for the customer to meet the actual runout specification. And then these components can go into further usage inside of the engines. So the overall process flow, to summarize how that works, is we start with our requirements in Peen Forming. We look at the treatment analysis of what's going to get us to those requirements. We'll then run through our process simulation, which uses our finite element process. Eventually, we'll actually do the treatment itself, and then our validation. This can be an iterative loop, especially if you have complex geometries that we're working with. So while the processing and simulation gets us very close, there can be some opportunities to further refine those results. So another similar example for correcting shapes. This is a steering rack. This is a steel component, and the gear teeth on this rack are induction hardened in order to improve their life. As I mentioned with other manufacturing processes, that induction hardening process creates another type of misfit strain and leads to distortion in this shaft. In this case, the manufacturer tried to compensate for the gear teeth hardening by hardening the opposite face. And while moderately successful, that still creates some other problems, as this is it's a challenging application. And because it's a non-uniform geometric cross-section, that creates some issues in creating a consistent process with induction hardening. So the question here is, can laser shock peening be used to correct that shaft deformation? So just walk through how we tested these. We had 2 separate groups of samples, approximately 10 to 12 shafts in each of these groups. One was kind of a standard group per the manufacturer. The other has some irregular properties to it. These have also, in some cases, been attempted to have the runout corrected through direct mechanical pressing methods, and that's failed. So how we measure the runout, basically we have our shaft between 2 pins. It is then spun, and we measure with a dial indicator what the runout is at each one of those locations along the shaft. For this product to be acceptable, we had to be under 100 microns of runout for the shaft. And as you can tell from the data, some of our samples that we received to test here were up to 1 millimeter of runout. As these are fairly large shafts compared to the crankshaft engines, there's a less sensitivity here. So instead of our 10 micron runout, over a span of 150 millimeters, we have 100 microns over an 800 millimeter. So how does laser peening potentially solve this issue, and how do you build a solution to the problem? So with laser peening, we're looking at providing a compensating eigenstrain to mitigate the distortion in the part. So we can specify a laser peening treatment area. We can vary the length of this area along the shaft. We can also vary the location of this peening area along the shaft, and then correspondingly predict the deformation that's going to occur from that treatment. If we want to look specifically at runout, that's a simple tweak to the boundary conditions within our modeling, shown in the bottom, and basically by looking at deformation in a different way, we're also able to calculate runout. So one of the unique things with this shaft is not everyone is bent in the same way. There's both convex and concave curvatures on the tooth side of this rack, so we have to have corrective treatments for both potential scenarios that we're going to encounter. So to correct for what we're treating as a negative bend, we can process the gear tooth roots, and that's going to cause the shaft to bow away from that curve, or from the tooth face. Alternatively, if we need to create a concave curvature on the teeth face, we can apply the patch to the opposite face. So what we have is the predicted deformation as a function of shifting these different patch locations on the right side of the screen. So if we use a 1-inch patch, we're able to vary the deformation along this profile by a treatment near the end. And that this is going to similarly change if we use 2 inches. So what we're basically doing is building out a library of options to create corrective peen forming treatments for these shafts. So since every shaft is different, what we really need is a broad solution that we can look at. So our technical approach for this application, we measure the shaft distortion. We then look at our simulation generated prescriptions for straightening these shafts. Basically, it's a pre-compiled recipe book. So if you have a measured shaft deflection, you can then select the prescription from this book that will best compensate for those measured deflections. We'll then process the shaft and then verify the corrective profile. For this initial implementation, what we've done is this is a single LSP treatment condition. So being steel, we're operating on up around 9 gigawatts per centimeter squared. And we just simply vary the location and size of the laser peening treatment patch. There's probably plenty of additional opportunity here to modify the intensity in order to optimize the solution further. But this initial work did not seem to be a necessary requirement. Just to give an idea, how long does it take to do this type of operation? So if we're looking at our 1 millimeter or 1 inch treatment area, basically at a 25 by 25 millimeter square, using our Pacuto 200 laser peening system, this is only going to take about 10 seconds. So if we consider a 30-second process window for a part, we can measure, process, and measure again to verify the process effectiveness, all within that 30 seconds. So this is the type of speed that is needed in production applications, and that's the direction that we're going with our laser peening systems. Ultimately, in this case, all of the runout on the shafts was reduced below our target level of that 100 microns. I didn't want to show every single shaft result here, just to be bombarded with data. These are some of the 4 worst cases of different types of profiles that were encountered with our measurement and correction process. So in all of these, we are now below that 100 micron runout level. So the next example I wanted to run through is a frame component for a helicopter. Similar to other manufacturing, this is machined out of a very large aluminum forging. So there's a lot of natural residual stresses present inside of this component. As you machine pockets inside of this frame, you are releasing previous residual stresses. As you're heat treating these, you're generating and releasing residual stresses. So it becomes a very complicated product to manufacture without having a distortion inside of it. So one question is, if you can manufacture it, can laser peening be used to provide a final correction to the shape to bring it into its designated tolerance bands? So our overall approach here is very similar to what we showed for the steering shaft correction. We will measure the distortion. We'll have our simulated processing correction guide for each of those distortions, provide the processing, and then verify the corrected profile. Now walking through all the data associated with this one, just wanted to show some of how this works. So if we assume a fixed intensity for our processing, and then just vary our treatment size, you can see the corresponding effects on this frame. So as the treatment in red here extends in length, it is causing this end of the frame to toe in. Our alternative, if this is not the deformation that we're trying to correct for, if let's say we have an out of plane bending issue here, or potentially twisting issues, what we can also show is if we assume a fixed treatment area and then we increase the treatment intensity, right, as we increase the treatment intensity, the bending will be increased. So those are just some of the tools that we have to play with in providing this corrective forming. As a summary, so we can use laser peening to engineer a corrective treatment for many different distorted components. We can't do it without modeling and simulation unless it's some of the most simple geometries that you could think of. But in the long run, all of the examples we've shown here are tooling free, right? So there is no special handling setups required in order to generate these corrective treatments. And this lets us do it in a quick time period and really at relatively low cost compared to other techniques. So the question coming out of this, right? Well, we can show how we can correct a profile. What does forming an actual product look like with laser peening? And that's where we get into laser peen forming for actual shape manufacturing. So there's several different variations that you consider in manufacturing the plates. Let's see if I can hide this menu bar at the top.
Stan, that's not showing on ours.
Okay, great. I want to make sure that titles are coming through. So in peen forming, we can have a couple different variations. There's free form, which is we're basically holding the part at some irrelevant location on the material. This lets the part free form as we apply each individual laser peening shot. The beauty of free forming really is that there's no spring back issues. Spring back is going to be, whenever you apply a elastic constraint to a component, when you release those constraints, it's going to bounce back as that constraint's released. If we need that, we can do the elastic pre-straining. This basically involves some type of form applied to the part, and it's really just another method of adjusting the peening process intensity. Also, it's preferentially applying the laser peening into your pre-stress directions. The final one is a combination. So laser peening is only going to be able to create gradual curvatures inside of materials. You're not going to be able to do any kind of stepped profile of actual forming, right? You cannot create a sharp corner with laser peening. Everything is going to be a nice gentle curve associated with it. What I want to talk about is the really free forming and some of the pre-straining for the next several slides. So here we just have a forward problem example for peen forming, where we're going to arbitrarily define a treatment for a panel. In this case, this is a large 4 foot by 6 foot aluminum 5000 series panel. And we can specify our treatment areas as I described using our eigenstrain model in the top left, evaluate our predicted deformation, shoot the panel, and then test it. So as you can see from the shapes, we're able to generate these complex compound curvatures in large structures, and it's controllable and accurate with these peen forming models. Just as another example, this is the same idea. Our forward problem of, okay, if we apply this treatment, what shape will be generated? This one is simply processing some corners, seeing how the rest of the panel responds. But it gets a little more interesting when we start talking about our inverse problem here. So if we have a desired shape that needs some level of specification to it. How do we get there? So the example that I'm going to walk through is just if we have a gore panel for propellant tank being manufactured, what does our process at LSPT look like of trying to define what our starting geometry looks like and what treatment conditions we need to use to obtain that shape. So in this case, what we do is start with a 2.5 meter hemisphere. We then break that into a quarter section and then trim it to our height that we need for our panel. We then use our modeling simulation software to force the final product into a flat state. And that gives us the starting geometries for our simulations, at least a initial product for us to work with. So what we can do in peen forming, in this case, this is a perfect application for laser peening because the compound curvature required for a dome is what laser peening is going to naturally put in to the processing. So we just simply simulate the laser peening on the top surface of this geometry that we decided was appropriate to start with. And then we can look at the deformation profile and then look at how it compares to the original shape. So this is a quick overlay of our target shape against the simulation predicted shape. So the blue is our pedal shape inserted into the initial. So in this case, what this tells us is that we probably need a slightly larger starting dimension that we started with, and potentially a slight increase in our peening treatment. But it's very close for an initial start, and it can be done without forms. So this becomes a viable manufacturing process. If you don't want the multi-directional elements, what can we do? That's where our elastic constraint examples come in. This is a relatively basic sample. If we have this peen formed shape and we want to constrain one direction versus the other, we can just apply a bending bar to the sample on the back surface. So in this case, what we see is by applying the bending bar in, call this our vertical direction here. This is clamped to the back surface of this material. Instead of achieving the 25 millimeters deflection that's happens out at the free ends, we're down to about 4 millimeters without adding any complex treatments. There are some other ways that you can get there besides the elastic constraints if you're looking for generating one-dimensional bend. And really that's, you can define some opposite surface treatments that will counteract the bending treatment, but that'll be a presentation for a different day. So how do we go about some of this modeling and simulation work? We can add some constraints into our modeling. With the eigenstrain modeling, we don't really have the elastic constraints set up to handle the spring back issues. So this can create some variance between the laser peening simulation and the actual end product. But if we take our sheet here, this is approximately a 2 foot wide by 5 foot long piece of aluminum. Without any kind of laser peening correction, we'll simply end up with a bit of a dished structure. Instead of what we want to reach is a complex curvature. We have a flat surface at one end of the panel that then is gradually curved up to the other end. How we do that, our work uses simple toolings in this case. So this is a wood formed based elastic constraint that was manufactured for this panel. So the panel is then mounted to our form, and we can progressively treat this sample. And using simple fixturing, just some clamps and straps, we're able to limit the deformation in certain directions that would otherwise be naturally occurring from laser peening. So as a summary, laser peen forming, we can create near net shape products just from laser peen forming. This is pretty revolutionary. It's a relatively new technology, but something that's going to be seeing a lot of growth in the future. But again, it requires the strong modeling and simulation capabilities to look at how do you solve the inverse problem of having a desired target shape and figuring out how to get there from laser peening. This is an area of growth that's going on, and I think this will probably be touched on by anybody else in their presentations as they discuss how laser peening can be used in forming and straightening. So I think I've got about 10 minutes left here, so I think I have just 2 slides remaining to go over, and that's kind of where we see the future of laser peen forming, what our challenges and opportunities are associated with the process. Every example that we walked through today followed the same general flow chart where we walk through collecting and measuring our data on a part, our requirements, seeing whether it needs to be treated and where that needs to be treated, conducting some simulations, testing, and then verifying the results in the end. The biggest weakness with this at the moment is that these are manual or potentially semi-automated processes for a lot of this correction. So there's not a lot of optimization that's been done at the moment. At least this is specific to a broad industry of laser peening treatments. So I think the continued growth in laser peen forming, we're going to start to see a lot of additional implementation of technologies in solving these problems that we're running into. And specifically, when we look at the further automation of the laser peening process, there's a lot of work being done right now in scanning data using point cloud mapping data, creating the feedback loops that'll help predict where components need to be processed rather than any physical measurements. Artificial intelligence and machine learning that are being incorporated into laser peening right now is a impressive field. There's a lot of work being done in optimizing laser peening. If that's not already incorporated into peen forming, it'll be there very soon. And it's something that we're internally working on developing as well. Most of the peen forming work that's been done in literature and in production, as far as general shape manufacturing from scratch, is aluminum based. There's some growing interest in titanium. We've done some work on titanium flight control surfaces. And obviously we've got a lot of work with our steel shafting corrections as well. None of these have necessarily been studied for what's the optimum bending, what's the optimum shape correction as far as economics. Process capabilities are generally well defined at this point, but there's definitely some room for further optimization in efficiency and potentially in the capabilities. And then how is this all done in the end, right? There's a lot of on-site system integration work that's going on. As the laser systems have been hardened for industrial applications, these processes can now be moved in-house, right? Creating a lot of challenges in really it's a further automation and simplification process. Okay, so where as LSP technologies, we have a lot of expertise in solving these problems. There's tribal knowledge, there's the simulation knowledge. Right? Building out these systems that can automatically solve these problems is going to be key for the future growth of the technology. So there's a lot coming up for peen forming. And I think there's a lot of growth that's going to be in this field, and I look forward to hearing what the rest of the team out there has to say as we listen to the other presentations today. So I want to say thank you for taking the time to participate. And with that, we've got about 5 minutes for questions.
That's correct, Stan. I want to say thank you for your presentation. I think some of the modeling work and efforts you've shown here in Demonstrator are really important for the advancement of laser peening and laser peen forming. Thank you. The question we do have, we have one in from Sergey Shabayov. He says, the question is, when calculating a final shape, do you vary the laser parameters or do you need to do that?
So I think I'll provide my interpretation of the question, because I think there's maybe some context to that. The final shape you may be able to achieve through a combination of parameters, depending on what's available, to your disclosure. For LSPT, our modeling relies on eigenstrain based simulations. Because of that, our eigenstrains are tied to specific treatments. So our process is still some of that forward problem. If we know what shape we need to achieve, we can represent certain conditions and test them to see if they will generate that desired shape. The actual most optimum to get there, that's a future modeling and simulation problem that really the only way to get there is going to be through some of the machine learning or potentially artificial intelligence implementations.
Great, thanks. I think we've got time. I'll take at least one more question. The next question comes from Nikolaya Kashiyev. In most applications, examples of presented, it seems that the LSP process was applied without protective coating. The question, I think, is how to form or reshape the component where very high requirements for surface quality or finish are targeted. If you apply the LSP process with a protective coating, or do you, the problem could be in overlapping areas, damaging the coating. And I guess what is your experience for such applications?
So we've done some of both types of work. The aluminum products that were shown were all formed without any type of opaque overlay. Those didn't have any specific requirements. Those are more of a demonstration piece. We form oxides in the laser peening process because of the thermal effects of the plasma. If it's necessary to maintain very tight tolerances on surface roughness, you can use the opaque overlays. The Wankel engine crankshafts, that was done using an opaque overlay, so we were able to not impact the we didn't create any thermal mechanical effects with that process. That's a purely mechanical finish. In the end, if we're bound to very tight restrictions, we still have to achieve a certain plasma pressure to generate cold work in the material and the subsequent forming. The level of those surface roughness modifications we can scale. Some of our customers we've worked with will provide final machining conditions to a part. I would say for most of our peen forming applications, the roughness induced by our laser peening hasn't created any issues in them being able to move forward with using them in production. But I can see in some cases that may be an issue. The titanium example I showed, because that's titanium, we don't process that bare. That's uses opaque overlay, and the indentations created on that surface from each individual laser peening spot are barely negligible, but that's also a rather high strength alloy.
Great, thanks, Dan. One last question. I think this is a short answer. We have about 30 seconds left. And this is from Jim Smith. What is the nominal spot size?
So the nominal spot size we use is based on our laser system that we're working with. Our aluminum peen forming, we've demonstrated from 1 to 6 gigawatts. To be the most optimum, you're going to use the maximum energy you have available. So, in our current Procuto 200 laser peening systems, that spot size is going to range from about 3 millimeters to 6 millimeters for most of our peen forming work.
Great. Well, thank you, Stan. Appreciate your presentation.